All right, here's the week for algebra. We have 3 book assignments, worksheet, and then a quiz. There's my email if you need to email me. All right, let's get started. First section is 11.4. Pencil. All right. This is on the Pythagorean theorem. A guy named Pythagoras made this cool theorem that works with right triangles. Right triangle, again, is a triangle that has a right angle in it. We label the sides A, B, and C. A and B are what are called legs. C is called the hypotenuse. C is always opposite the right angle. The formula for Pythagorean theorem is a squared plus b squared equals c squared. And again, like I said, this only works for right triangles. All right, so let's do a few examples. Solve for x. Now the first thing you want to do is figure out where is the hypotenuse. And again, the hypotenuse is opposite the right angle. The right angle is signified with a box. So opposite this box is x. So x is the hypotenuse. So we'll put that on the right side of the equation. The other two sides are the legs. It doesn't matter the order you write them in. Remember, it's a squared plus b squared, or in this case, 9 squared plus 12 squared. 9 squared is 81. 12 squared is 144 equals x squared. We're going to combine like terms to get 225. And again, we're solving for x, so now we need to cancel out the square. To cancel out the square, we're going to square root both sides. And the square root of 225 is 15. Now, when you square root a square, you technically have absolute value of x equals 15, and then x equals plus or minus 15. But in this case, x is representing a length, and a length has to be positive, so we're going to reject the negative 15. You cannot have a negative distance, so that is what is called an extraneous root. So when you're doing these problems, you technically do not have to show these two steps where you're have the absolute value plus or minus, because we know that in all these problems we're rejecting the negative anyways, because we have to have a positive distance. Next example. Again, first thing you want to do is figure out where is the hypotenuse. The hypotenuse is, again, the side opposite the right angle, and in this case 17 is the hypotenuse. So we're going to put that on the right side of the equation. Again, it doesn't matter with the other two sides which one you write first. I like to write the variable first. So x squared plus 15 squared equals 17 squared. 15 squared is 225. 17 squared is 289. And we bring down the x squared. Now, this problem, unlike the last one, the numbers are on opposite sides of the equals. So now we have to use algebra to solve this problem. So to get rid of this positive 225, we need to subtract 225 from both sides. Cancel. X squared equals 64. And again, like the previous problem, to cancel out a square, we will square root both sides. And again, like I said, we could probably ignore the absolute value of x and then the plus or minus, because again, we know the answer has to be positive. So the square root of 64 is 8. Let's try one more example from these directions. Again, this only works with the right triangles. All right. Again, the first thing you want to do is figure out what the hypotenuse is. The hypotenuse, again, is opposite the right angle. So the side opposite the right angle is square root 6. So we put that on the right side of the equation. Now, if you notice, they only give you one measurement of one of the legs, but these tick marks, if you recall, mean that the two sides are congruent. So if this side is x, this side down here also has to be x. So again, we have x squared plus x squared equals the square root of 6 squared. X squared plus x squared is 2x squared. The square root of 6 squared is just 6. The square and square root cancel out. We divide by 2, and we get x squared equals 3. Next step is to cancel out the square, so we will square root the square. The x cancels out, and we just get the square root of 3. We could make that a decimal, but there's no need to. If anything, it's better to keep it as the exact answer, which is square root 3. All right. With right triangles, we have what are called families. The most common or most popular family is what is called the 3, 4, 5 right triangle. What that means is that any multiples of 3, 4, and 5 together will give you a right triangle. So if we multiply each of the sides by 2, 6, 8, 10, we know that's a right triangle because it's part of the 3, 4, 5, and all I did was multiply each side by 2. If we multiply each side by 3, that would give me 9, 12, and 15. So 9, 12, 15 is a right triangle, and I don't need the Pythagorean theorem to figure that out. There are other families. In geometry, you probably need to know 4 of them. 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17. You'll find for the rest of the chapter, when I give examples, it'll probably be one of those 4 families. Again, if you look back at the second example we did here, this is the 8, 15, 17 triangle. Even the first one, there's the 9, 12, and 15. That's just the 3, 4, 5 multiplied by 3. All right, so anyways, what we're going to do in this example is they're going to say the following problem is part of the 3, 4, 5 right triangle. AB is the longer leg. There's 2 questions. What's BC? And what's AC? So again, we have a right triangle here with AB being 14. All right. So again, they said that AB is the longer leg. So the longer leg in the 3, 4, 5 is the 4. Remember, 5 is the hypotenuse, so 4 is the longer leg, 3 would be the smaller leg. So I need to figure out how many times larger 14 is than 4. All right, so basically 4 times what is going to give me 14? Or another way of saying that is 14 divided by 4 is what? And that would be 3.5. So this triangle is 3.5 times larger than the 3, 4, 5 right triangle. So then we have to multiply each of the sides by 3, 4, 5, I'm sorry, by 3.5 to get the dimensions of the other two sides. So 3 times 3.5 is 10.5. And that would be BC, which is the small leg. So that's the answer to the first question. And then 5 times 3.5 is 16.5, which would be AC, or the hypotenuse. And that's the answer to the second question. The next part we'll ask, is the following a right triangle? If you know your families, you would probably know the answer to this problem right away, but it's not always the easiest to memorize those common families. So how you determine it is you use the Pythagorean theorem and see if they are equivalent on both sides. We will always make the largest number the hypotenuse, because the hypotenuse has to be the largest number. So we use the Pythagorean theorem, we put the biggest number on the right side, and again, it doesn't matter the order of the other two sides. We square each of them and see if we have equivalent numbers on both sides. If we do, it is a right triangle. If we don't, it's not a right triangle. So 8 squared is 64, 15 squared is 225, and 17 squared is 289. We add these two numbers together to get 289, and as you can see, these are equivalent. Therefore, this is a right triangle. Let's try one more example. 6, 8, 12. So again, we make the largest number the hypotenuse. So we put that on the right side. That would be the 12. Again, it doesn't matter the order that you write the other two numbers on the left side. 6 squared is 36. 8 squared is 64. 12 squared is 144. We add these two numbers together to get 100. And 100 is not equivalent to 144. Therefore, this is not a right triangle. And that's the first section. .5 deals with operations with roots. More specifically, we'll be looking at square roots. All right, we have a ton of examples in this section, and for most of them, the directions are just going to be to simplify. In this section, we probably wouldn't be using the calculator a lot. All right, so simplify means write as little as possible, but have an equivalent expression. Don't do any rounding, and make sure that our radicals or our square roots are simplified down as best they can. All right, so the first example, we have 4 square root 2 plus square root 2. Again, if there's no number in front of the square root, that number is a 1, just like variables. If this was 4x plus x, the answer would be 5x. Well, this is done very similar to that. 4 square root 2 plus 1 square root 2 would give you 5 square root 2. Again, we do not want to change the square root 2 to a decimal. We want to keep it as a square root. And that's the answer. Before you circle it, you just double check your radical or your square root and see, can we pull out a perfect square out of there? And square root 2, no, that is done. Square root 5 times square root 5. All right. With square roots or any other radical, you multiply the number inside the radical and you keep the square root symbol on it. So we can multiply 5 times 5, which is 25, and we keep the square root symbol on it. Now we check to see, can we simplify this number? And the square root of 25 is 5. Square root 3 times square root 2 times square root 3. Again, like the previous problem, we said we can multiply all the numbers inside the radicals and just keep a radical symbol, or in this case, a square root symbol on that number. So we can multiply 3 times 2, which is 6, and then 6 times 3, which is 18. And then we put the square root symbol on it. Now we need to check, just like all the other problems, can this be simplified? Can we pull a perfect square out of that number? Again, if you remember, perfect squares are the products of the same number multiplied by itself. So for example, 1 times 1 is 1. So 1 is a perfect square. 2 times 2 is 4, so 4 is a perfect square. 3 times 3 is 9, 4 times 4 is 16, and this goes on forever. So I look at square root 18, and I always want to work from biggest number to small, because I want to pick the largest perfect square that can be pulled out of there. So I don't try any numbers that are bigger than 18. The first number I would technically try is 16. 16 doesn't go in 18 evenly, so that doesn't work, but 9 does. All right. 9 times 2 is 18. So this breaks down to square root 9 times square root 2. And the square root of 9 is 3. The square root of 2 doesn't break down, so we just bring that down. So the answer is 3 square root 2. In the next example, we are doing subtraction and addition. Now, similar to variables, you can only add or subtract like terms. So the square root 3 and the square root 2, we can't combine to get a smaller answer. So when we look at this problem, we look for like terms. That's the same number inside the square root symbol. So this 4 square root 3 can be combined with negative 7 square root 3. And just like variables, we're going to combine the coefficients and keep the variable, or in this case, the radical, the same. So 4 minus 7 is negative 3, and we're going to keep the radical the same thing, square root 3. It doesn't become square root 6. It doesn't cancel out. It's just like x. 4x minus 7x is negative 3x. Now I look at the square root 2's. I see a negative square root 2 plus 5 square root 2. Again, if there's not a number in front of the radical, that coefficient is 1. So really what we have here is negative 1 plus 5. Negative 1 plus 5 is 4. And like we said before, we're going to keep the radical the same. So it's still square root 2. So the answer is negative 3 square root 3 plus 4 square root 2. You cannot add square root 3 with square root 2. Those are not like terms. Square root 3 times the sum of square root 2 and square root 3. Again, this is a multiplication problem, so we can multiply those numbers inside the radical. So we're going to distribute the square root 3 into both terms. Square root 3 times square root 2, again we can go 3 times 2 is 6, and put a square root symbol on it. So if 3 times 2 is 6, the square root 3 times square root 2 must be square root 6. And then we do it with the second term. Square root 3 times square root 3 is square root 9, and the square root of 9 becomes 3. Now a little shortcut with that is that if it's the same number inside the square root, the answer will just be that number. Like if we look at letter B, square root 5 times square root 5 was 5. Square root 3 times square root 3 is just 3. Again, this is addition, so we cannot add square root 6 to 3, and we can't pull out a perfect square with square root 6, so this problem is done. Let's look at division. If we can multiply the numbers inside the square roots, we can also divide them, because division is just the inverse of multiplication. So if 28 divided by 7 is 4, the square root of 28 divided by the square root of 7 must be the square root of 4. And the square root of 4 can simplify down to 2. The next problem, square root 7 times 2 square root 7. This is just, again, one big multiplication problem. What I like to do is first figure out what the coefficient is, or the big number in front. Again, if there's no number in front of the radical, it is a 1. 1 times 2 is 2. Now I'm going to look at the radicals. Square root 7 times square root 7, remember, it just becomes that number inside. You could say it's square root 49, but then the square root of 49 becomes 7. And again, since this is a one big multiplication problem, we're going to put a multiplication sign between those two numbers. And 2 times 7 is 14. Now we're going to look at a few expressions that doesn't have an operation with it. Square root of 75. First thing I would do with a number that's a little larger is figure out, is it a perfect square? So we could check that on the calculator, and the square root of 75 is not a perfect square. So now we want to find the largest perfect square that divides into 75. So again, we look at our perfect squares. The first number I would try is 64. 75 divided by 64 does not work out evenly. I try 49. 75 divided by 49 does not work out evenly. Try 36. That does not work. But when I try 25, that does work. 75 divided by 25 is 3. So the square root of 75 becomes the square root of 25 times the square root of 3. I would always write the perfect square first, because that's the number that's going to change. The square root of 25 becomes 5. The second number will never change as long as you pulled out the largest perfect square. So we're just going to bring down that square root 3, because again, there is no number that we can pull out of square root 3. So the answer is 5 square root 3. square root 12. Again, square root 12 is not a perfect square. So we look to see what perfect square we can pull out of there. First perfect square we try is 9. 12 divided by 9 does not work out evenly. Then we try 4, and that does work. So 12, the square root of 12, breaks down to the square root of 4 times the square root of 3. And the square root of 4, again, is 2. And then we bring down the square root 3. So the perfect square always breaks down one more step, where the other number just tags along. So the answer is 2 square root 3. Square root of 81. Again, the first thing you should check is to see if that's a perfect square. Well, the square root of 81 is a perfect square, so the answer is just 9. The square root of 98. We check to see if that's a perfect square, and it isn't. So we look to see what's the largest perfect square we can pull out of there. So we try 84. That doesn't work. 64 does not work. 49 does. So again, we write the perfect square first. 49 into 98 is 2. So the square root of 98 becomes the square root of 49 times the square root of 2. And the square root of 49, we can always simplify, and that simplifies down to 7. The second number will never be simplified any further, so that just comes down. So the answer is 7 square root 2. Square root 3 times the sum of 6 square root 2 and 4 square root 3. Again, we have a number outside the parentheses, so we are going to distribute or multiply the square root 3 into both terms. This one's similar to letter G, where we should multiply the coefficients first and then figure out the radical. Again, since there's no number in front of the radical, we know that it's a 1. So when I multiply the coefficients, 1 times 6 is 6. Now I'm going to look at the radicals. We can multiply different numbers inside the square roots. So the square root of 3 times the square root of 2, we did that problem way back in C, is square root 6. We cannot break that down any further, so that part is done. Now we repeat the process with the second term. We multiply the coefficients first. 1 times 4 is 4. And then we multiply the radicals. Square root 3 times square root 3, we've seen that before in letter E. That just becomes 3. And again, that's multiplication between those two numbers. So that becomes 4 times 3. Now again, the directions say simplify. So we need to shorten this up as much as possible. Well, we can do 4 times 3. 4 times 3 is 12. We bring down the radical. And like we said before, we cannot add radicals with numbers. So this problem is done. Last example. 12 plus or minus the square root of 48 divided by 4. So the first thing I would do is figure out what the square root of 48 is. I'll do that off to the side. So I check to see, is that a perfect square? And the answer is no. So now I'm going to look for the largest perfect square to pull out of that. So I do not start from the left. 4 actually does divide evenly into 48, but I need to find the largest number that divides into 48. So I need to start on the right side, not the left side. Again, we don't try any numbers bigger than it, so the first number I would try is 36. 48 divided by 36 does not work out evenly. 48 divided by 25 does not. But 48 divided by 16 is 3. So the square root of 48 becomes the square root of 16 times the square root of 3. Again, I write the perfect square first because that's the one that will always break down, where the other number will never break down. The square root of 16 becomes 4, and the square root 3 tags along for the ride. Now I can put the 4 square root 3 where the square root 48 was. So I rewrite the problem, 12 plus or minus 4 square root 3 over 4. Now all 3 terms are even, so they can be divisible by 2. But we want to find the largest number that you can divide all 3 terms by. 4, 4, and 12 are all divisible by 4. So I am going to divide each of those 3 terms by 4. 12 divided by 4 is 3. Plus or minus comes down. 4 divided by 4 just cancels out, so you're left with square root 3 as the second term. And at the bottom, 4 divided by 4 is 1, but we never want to write 1 in the denominator when we are simplifying. So what we're left with is 3 plus or minus the square root 3. And again, we cannot add radicals with numbers. So we are done. And we are done with this lesson. Third lesson, 11.6, is on the distance formula. The distance formula is the difference of x's squared plus the difference of y squared. You add them, and then you square root it. So let's find the distance